Okay, hello everyone. Thank you for joining the 5th webinar of the Reframed Tech Series presented by the Pembina Institute's Buildings and Urban Solution Program. My name is Ghazal Ibrahimi. I am a senior analyst at Pembina and I have the pleasure of moderating this session today. Pembina is a national nonprofit clean energy think tank with offices across Canada. I'm here today from Vancouver, the traditional lands of the Coast Salish people, Musqueam, Tsleil-Waututh, and Squamish nations. We work on policy in the areas of renewable energy, clean economy, oil and gas, buildings, and transportation. Pembina is wanting to thank our funding partners, Natural Resources Canada, Federation of Canadian Municipalities, and CMHC, and our supporting partners, Real Estate Foundation of BC, SICA Foundation, and North Family Foundation. Moving on today's webinar, I'm joined by my colleague Stephen Hoy, who is helping ensure today's webinar is a success. Stephen is producing the Reframed Tech Series and leads our communications here in Vancouver. Here you see today's agenda. I will start by introducing our retrofit project and each of today's speakers. Then we move into the presentations, followed up by Q&A. And finally, I will leave you with information about an upcoming demonstration project opportunity. Just some housekeeping notes. A reminder that this webinar is being recorded and will be published online, which we invite you to share with your networks. To ensure high sound quality, all participants are muted throughout the webinar. To ask questions, please type them into the questions box on the GoToWebinar panel throughout the session. And we will try to answer as many of them as possible during the Q&A after all of the presentations are completed. I'm pleased to introduce you to Reframed Initiative. Through Reframed, we are working with designers, builders, owners, financiers, and policymakers to scale up deep retrofits. We believe that by bringing all of the players together to accelerate and improve retrofits, we can address our housing crunch and the climate emergency at the same time. Deep retrofits go beyond energy savings. They are healthy spaces, they are resilient and protect their occupants in extreme weather and seismic events, and they are low carbon. Scaling up retrofits is not an easy task, and we have to keep these goals in sight. We need to keep rent affordable. We need to minimize tenant disruption, particularly in cities like Vancouver, where the vacancy rate is below 1%. And we need the energy efficiency investment return value to the owners and investors. Here is a screenshot of our website. Please visit reframedinitiative.org, where you can find latest information about this initiative, and you can register yourself if you are interested to participate and respond to the RFP and receiving updates. To get everyone on the same page, we created a primer for today's webinar. It's available for download in the Handout section of your GoToWebinar panel. The primer will be also posted online together with the recording of today's session. The primer highlights the importance of addressing embodied carbon as we look for building retrofit solutions. It briefly describes several building retrofit strategies for reducing embodied carbon and explains why and how embodied carbon is becoming the dominant source of building emissions in certain areas. We are hoping that the primer kickstarts further discussion. Now to introduce today's speakers joining us from across Canada and the US, starting with Anthony Pack, Principal at Periopta and founder of ECN Vancouver. Anthony is the principal at Prescriptive, a life cycle assessment consulting firm that is one of the first in North America to offer a custom parametric LCA service for new construction projects. He is also the founder of ECN Vancouver, the first local chapter of the Embodied Carbon Network, which organizes local events that empowers building industry professionals to champion the topic of embodied carbon on their projects and within their firms. Since April 2019, ECN Vancouver has inspired over 20 other cities to start local chapters, and now Anthony serves as a regional director supporting local chapters in Western North America, Asia, and Australia. Anthony is a professional engineer with a master's in industrial ecology from NTNU, which is a leading LCA research group in Norway. Thank you for joining us today, Anthony. Our second speaker is Lindsay Rasmussen, Program Manager at Architecture 2030, who is joining us from Santa Fe, New Mexico. As a program manager with Architecture 2030, Lindsay is dedicated to reducing carbon impacts of the built environment. She has developed and managed several of Architecture 2030's education initiative, most recently the Carbon Smart Materials Palette and the highly successful AIA Plus 2030 online series. Lindsay is a certified Passive House consultant, an advisory member of the AIA Materials Knowledge Working Group, and a member of the Embodied Carbon Network. She recently advised a University of Oregon and Tollwood Design Institute research project on cross-laminated timber and its availability, benefits, and barriers, applications, and embodied carbon impacts. Lindsay holds a Bachelor of Architecture with a minor in Environmental Studies from the University of Oregon. Thank you for joining us, Lindsay. Our next speaker is Graham Stewart, Principal at ERA Architects and Center for Urban Growth and Renewal. Graham is a Toronto-based architect and urban planner, a principal with ERA Architects, where he has contributed to many of the Toronto's region's leading urban design, cultural planning, and revitalization projects. Graham is also a founding director of the Center for Urban Growth and Renewal, Cougar, an interdisciplinary urban research organization founded in 2009. Working with NGOs, academic, government, and community partners, Cougar supports policy and action toward more equitable and resilient urban regions. The key focus of this work is Tower Renewal, a multi-sectoral initiative focused on the low-carbon future of the many thousand mid-century tower block found throughout urban Canada, which he will be talking to us about it today. Graham is a member of the Toronto Community Housing Design Review Panel and is a regular lecturer in universities in Ontario and abroad. Thank you for joining us, Graham. With that, I invite our first speaker to the screen. Anthony, over to you.
Hey, everyone. Oh, hi, can everyone see my screen? Or I'm hoping so.
Yes, all good.
Okay, great, perfect. Okay, thank you very much for inviting me for this presentation and for everyone for attending. I'm going to be talking about embodied carbon, giving a quick overview of embodied carbon, why it's important, and also some of the design strategies that are relevant for retrofits. So first off, what are we talking about when we refer to embodied carbon? We're really looking at the emissions associated with construction materials used in buildings. So think of all the materials used in buildings, the concrete, steel, wood, glass, insulation. All of those materials have impacts. And so they're often actually hidden from us. You know, the energy side of things, it's very easy to kind of measure and quantify. But when it comes to the materials, we actually have to think through what are the emissions associated with extracting those resources, transporting them, manufacturing, processing, construction, operation, and also end of life. So this is a big deal because if you actually look at global emissions happening annually, about 28% of emissions of global CO2 emissions is attributed to building operations. So that's heating and cooling and operating all of the buildings on the planet. That's 28%. The embodied carbon annually is about 11%. So that's all the new construction and major renovations that are taking place each year. That's about 11%. But what's interesting is, many people have seen that statistic, but there's also this this great chart from the World Green Building Council that recently got released, which looks at the impacts of even 3 key materials that are used in buildings: concrete, steel, and aluminum. And if you look across all 3 of those materials, that accounts for 22.7% of global emissions. Obviously, these materials aren't just used in buildings, they're also used in infrastructure, in cars, and other products, etc. But as the construction industry, if we can actually create demand for low carbon concrete, steel, aluminum, and other products, it has a ripple effect in other industries as well. So when we're talking about the impact of our industry, it's actually larger than even that 11% slice from an embodied carbon perspective. Now, if you just look at the new construction that's taking place between now and 2050, so over the next 3 decades, that amount of building stock, we will be, the embodied carbon will account for approximately half of the emissions, the overall emissions of that building stock, and that's over this lifespan, versus 51% for operational carbon. This is a picture of or kind of a simplified representation of the emissions throughout the lifespan of a building. So the yellow bars, you can see that's the emissions happening each year to operate the building, and that's what we've obviously been focused on with our retrofits or with our energy efficient designs of new buildings to get this number down. But there's also the red portions, and that's the emissions associated with the embodied carbon. So there's a big chunk pulse of emissions up front, and then there's also the emissions associated with replacements and maintenance of certain building components and materials, and then also certain emissions associated with end of life. This is what the formalized definitions of each of the life cycle stages are. So when we're talking about embodied carbon, the way we quantify it is through life cycle assessments, LCAs. And so within each, this is what we mean by life cycle stages. Each of these life cycle stages, from raw material extraction or supply, transportation, manufacturing, they all have different stages. So the A stage is the upfront carbon. The B stage is the use phase, so the building operation. Incidentally, the B6 portion, that's operational energy use. So that's the portion that we've been very familiar with: energy modeling, operational carbon emissions, etc. And then there's the end of life portion. So all the emissions associated with deconstruction, transportation, waste processing, disposal. And then there's a module D as well, life cycle stage D, which deals with benefits and loads beyond the system boundary. So how do you account for things like recycling, reuse, where you don't kind of include double counting in a way. So we usually report that separately as well. Now, how does embodied compare with operational carbon emissions? In the operational world, we're very familiar with energy metrics, energy use intensity, EUI, but we oftentimes use that as a proxy for carbon emissions, but it's not always the best proxy. So if you look, this is from the CAGBC's report. The dark green bars show you baseline building performance, operational greenhouse gas intensities. And so you can see it varies significantly, right? Like Vancouver might be 20, Toronto 26, Calgary could be like 71, which is partly due to the higher grid intensity of the carbon intensity of their electricity grid. So these are just for kind of baseline buildings. However, if you go towards higher energy performance buildings in Vancouver, we can get much lower numbers. So here's an example of those lower numbers. So this was a great study done by Integral Group looking at the BC Energy Step Code. So you can see for each of the steps, step 1 to step 4 or 5, obviously the operational greenhouse gas intensities are going down, but actually the big factor to greenhouse gas intensity reductions is fuel switching. So all the green bars refers to natural gas or hybrid systems, whereas the blue bars are electric. So you can see obviously the electric ones are significantly lower. They're below 2 kilograms of CO2 per meter squared at any step, versus the natural gas ones are, let's say, 4 to 13. But still, even the natural gas numbers, these numbers are quite low relative to other cities and other regions. So now you have some sense of like the operational carbon intensity, and this was just a picture of the variance in the carbon intensity of the electricity grid in different provinces. BC, Quebec, Ontario, we have quite a bit of renewables. So in BC, a lot of hydro, and so we have about 12.9 grams of CO2 per kilowatt hour. Very clean. So typically below 50, that's like renewables, mostly dominated by renewables. But then on the flip side, you have Alberta, for example, that has a lot of coal, that's the black portion, and natural gas, that's the red portion, and it's how it's evolved from 2005 to 2016. You can see Alberta is around 790 grams of CO2 per kilowatt hour. So it matters a lot, like the carbon intensity of the grid, and also the trend lines, like are these grid intensities reducing over time, and how does that factor into our operational emissions? So that was the piece on operational. That's just to give you some context when we're comparing those numbers with Embodied. This was a study done by the Carbon Leadership Forum that looked at over 1,000 whole building LCAs globally. And you can see for different building types, generally the range is anywhere from, let's say, for the bulk of the buildings, it's anywhere from 100 to 1,000 kilograms of CO2 per meter squared, with many of them falling in the range of, let's say, 200 to 600 kilograms of CO2 per meter squared. So you compare that with the operational numbers, because in BC, we've gotten our operational greenhouse gas intensity so low, especially if they're electric buildings and step code, it's below 3 kilograms or below 2 kilograms of CO2 per meter squared. These numbers become the dominant factor. The City of Vancouver, with our rezoning policy, which affects a lot of the new construction in the city, mostly requires calculation of embodied carbon. So for example, if you go through Path A, that's where you're using some low carbon or near zero emission building standards. So things like Passive House certification or CAGBC's zero carbon building standard or ILFI's standards as well. Many projects go down the Path B approach, where all of the buildings need to do a whole building LCA, and they need to report it at the rezoning stage, the building permit, and the occupancy permit stage. At this stage, they just need to disclose the results, but in next year, I think they're going to update the rezoning requirements, where they'll likely have some sort of reduction requirement. Additionally, if it's not a residential building, you also need to go for LEED Gold. And so the LCA and looking at embodied carbon is one of the strategies that oftentimes teams overlook, but you can get up to 5 LEED points through pursuing those credits, depending on the percentage of embodied carbon reduction potential there. So for all of these standards, for CAGBC zero carbon, building standard, ILFI, LEED, they have some requirement, or it's relevant to quantify and reduce these embodied carbon emissions. Now I'm going to get into some of the design strategies, and in my typical presentation, I go through a lot more different materials like concrete, steel, etc., and wood. But in this case, I'm just given the time constraints, I'm focusing on some of the key materials as it pertains to retrofits. So glass, aluminum, insulation, refrigerants, mechanical equipment, and interiors. So for glass, typically glass, we use large quantities of glass, obviously, in the building. Whenever you're dealing with anything envelope related, it's important to look at the trade-off between embodied carbon and operational carbon. It may not actually be a trade-off, but you just look at how to optimize across both of those domains, right? Obviously, if you, for instance, have triple pane windows, that's another pane of glass versus double pane windows. But generally speaking, what I've seen is that the glazing is not a huge component of the overall impacts typically. The frame actually is a big factor though. So it's not necessarily the glass, although there's obviously emissions associated with that, but pay attention to the framing options that you're using. Typically curtain wall assemblies are actually the highest embodied carbon impacts out of the different wall assemblies from what I've seen. If you go towards, and that's partly due to a lot of the aluminum mullions. But if you go towards timber framing, that can reduce the emissions a bit. Segueing into aluminum, aluminum is a very high emission intensity product. It requires something like 10 times the amount of electricity as opposed to steel. So given that it's an electricity driven process, it matters where this aluminum is produced. So for instance, in BC, because we have a very clean electricity supply, the aluminum that we produce is likely going to be very low carbon intensity, although I haven't seen EPDs for this, environmental product declarations, but generally speaking, we should have pretty clean aluminum. It's also very highly recyclable, but just know that even though it's very highly recyclable and there is a strong market for it, and we do typically recycle, there's not enough recycled aluminum to meet demand. And so, so generally speaking, try to use aluminum sparingly and use it with reuse in mind. Now, before I kind of transition to the next topics, some of you may have seen this book before. It's called Drawdown. They actually looked at the top solutions to climate change, to reducing emissions globally between now and 2050. And so many people will probably think of things like, oh, solar or wind or different renewable technologies as kind of the top solutions. But actually the #1 solution that they came out to in their original analysis was refrigerant management, which was very shocking to me and to a lot of people. They estimated roughly 89 gigatons of CO2 over the next 3 decades, which is equivalent to roughly like 2 years of annual CO2 emissions, which is quite a bit by itself. In contrast, if you think about embodied carbon, we oftentimes talk about concrete. Their quantification of the emissions reduction potential for alternative cements was in the order of 7 gigatons of CO2. So it's interesting that refrigerants were so high. Now, what's interesting is whenever you see any sort of CO2 related statistics, whether it's from the IPCC's reports on global climate change, all the way down to national reporting statistics, they're actually using what's called GWP 100, which is evaluating a range of different greenhouse gases and making them equivalent to CO2, but over a 100-year time horizon. And this makes sense because CO2 lasts in the atmosphere for thousands of years, and other greenhouse gases can last even longer. However, there are also some greenhouse gases that last much shorter. So, for example, in methane, you may have heard that methane is 28 times higher impact than CO2. But over a 20-year time horizon, it's actually 84 times higher. So it's actually about a 3x difference depending on which metric you use. And the same is true for different refrigerants. And why this is important is because methane, the lifespan is something like 14 years. For most refrigerants, HFCs, hydrofluorocarbons, they're about under 20 years for many of these refrigerants. So looking at a GWP 20 metric, you actually see for many of these refrigerants, they're 2 to 3 times higher than even the emission figures that we typically use in all of our calculations. So that means if we actually reduce these emissions, we have a very immediate impact on climate change, much more so than actually even CO2 in a way, because when you decrease these emissions, they kind of stop having an impact on global climate change more immediately. So it helps us avoid tipping points, etc. So why I'm bringing this up is because we actually use those HFCs not just in blowing agents, or sorry, not just in refrigerants in our HVAC equipment, but also in our insulation. So for example, if you actually look here, this is in particular XPS insulation and spray foam insulation. In North America right now, it's mostly using HFCs. Actually, I think for XPS, we only have HFC blowing agents for those. And remember those life cycle stages I mentioned earlier? Module B is a big chunk of those emissions. So for most materials, they're typically inert and they're not really emitting emissions, but with the exception of these ones which have blowing agents. And so if you look at the LCA studies, the EPDs from these different manufacturers from Dow and Owens Corning, you see that they actually have pretty significant emissions at the operation phase and also at the end of life stage. And why I bring this up is because some of these emissions have been underestimated in our whole building LCA calculations. So the 3 main tools that are typically used in North America, Athena, Tally, One-Click LCA, what I've seen is that some of their XPS entries or all their XPS entries oftentimes are about 10x lower than the numbers straight from the EPDs from these different suppliers. And part of it may be due to how they accounted for HFCs and et cetera. But generally speaking, if you just look at the top half of this graph, you look at this is the embodied carbon of many different types of insulation from R5 to R60. So for example, for XPS, it's R5 per inch. So R5, that's 1 inch, R60, that's 12 inches of XPS. You can see as you get up to 12 inches of XPS, depending on the compressive strength, you can get up to 1,000 kilograms of CO2 per meter squared of envelope area. And so compare those numbers with the whole building LCA numbers that I mentioned earlier, and you can see why these numbers are quite significant and how some of our previous LCA studies, if they have XPS and spray foam in them, they may have actually underestimated these emissions quite a bit. Below here, I have mostly industry average EPDs from EPS, from polyiso, GPS, mineral wool, fiberglass, cellulose. So you'll see I'll send out these slides afterwards so you guys can kind of look at this. So for most other insulation types, there's differences between them, but they're quite a bit lower compared to some of these top line categories. Now, there is going to be new HFC regulation coming in Canada and certain US states starting in January 1st, 2021. So there will be alternative XPS and spray foam that uses lower global warming potential blowing agents. So make sure you specify that if you're in those regions. Or actually just in general, you should specify that. I may be actually going a little bit over time. So in terms of refrigerants, we need to worry about the global warming potential of different refrigerants and also the leakage rates. And so there's a lot of uncertainty as to the percentage of leakage rate happening each year. So I've seen figures that are, let's say 2%, sometimes up to 10%. But then I've also heard anecdotally, sometimes in HVAC systems, when they leak, it just leaks the whole system. So then you've actually lost 100% of the system. So we need to get a handle of these leakage rate data. But for instance, in this example for a 1-ton heat pump in a 500 square foot apartment in New York, if you were to leak 100% of it, that would equate to around 60 kilograms of CO2 per meter squared. This is also exemplified in another study looking at a passive house building, but they were looking at mechanical equipment. This is in the UK. So they're comparing gas boilers to air source heat pumps and VRFs, variable refrigerant flow. So for instance, for variable refrigerant flow, typically the emissions are quite low, but if you account for it, depends on what the global warming potential of your refrigerant is. So I think this is R410A, assuming a 10% annual leakage rate. So if that was leaking that much, then this VRF under the high scenario can be like 2.4 times higher than the gas boiler scenarios. So these assumptions do matter significantly. So when you're doing retrofits, think about your refrigerants, what type of refrigerants you're using, and also the leakage rates. And then that was just on the refrigerant piece, but when you're talking about mechanical equipment, we typically don't include this in the scope of our whole building LCA calculations because we're mainly focused on structure and envelope. But and there's not really good data for instance, mechanical equipment. But in this study from the Carbon Leadership Forum, they tried to estimate the MEP systems, and let's say the medium case scenario is around 60 kilograms of CO2 per meter squared. That's for all the sheet metal, the duct, the mechanical equipment with the pipes, the embodied carbon associated with that. Same thing with tenant improvements. So all the interiors, the cubicles, the furniture, etc. That's, let's say, around 90 kilograms of CO2 per meter squared. And that's for each replacement cycle. So if you have a 15-year replacement cycle for your MEP and for your interiors, over the lifespan of a 60-year building, those MEP and TI systems can actually be more than the initial embodied carbon in the structure. So again, these are, while we don't typically factor this in most of our LCA studies, this is a big factor and it's something that we need to look at as well. Finally, this is a great roadmap from the Carbon Leadership Forum, looking at how to incorporate embodied carbon considerations throughout all the different stages of the project, from schematic design to design development, construction documents, bidding, construction, etc. So generally speaking, you want to integrate this just like energy modeling. You want to integrate it early in design. You want to evaluate different design options. And as you get to later stages, you might evaluate more manufacturer-specific EPDs or like low carbon sourcing, or sorry, low carbon material supplier sourcing. But yeah, I highly recommend you check it out. In many of my slides, I have links at the bottom, so feel free to click those to see the original sources. And finally, just one more thing. Our company, we're very focused on driving radical reductions in embodied carbon globally. This is our passion, this is our mission. So if you're working on projects, you need to do LCA or you want to understand embodied carbon, please feel free to reach out. Happy to help. And that's it for me.
Great. Thank you so much, Anthony.
Yeah,
very useful. No problem. Very useful to see how embodied carbon compares with operational carbon emissions in buildings, considering the carbon intensity of the electricity grid. I personally find it very important to highlight why we really need to have these discussions and think about embodied carbon in our building design processes. And also very useful to hear from you what are some specific design strategies that can help us reduce embodied carbon in building retrofit in particular. Thank you very much for your presentation. With that, I am going to invite our next speaker to the screen. Lindsay, over to you.
Great, thanks. And let me know if you can hear and see my screen.
All good, yeah.
Perfect. All right. Hi, everyone. Thank you for having me. I'm thrilled you're here and wanting to learn more about embodied carbon reductions. And I'm thankful for Anthony for introducing embodied carbon and providing a lot of great resources and great opportunities for reduction. I wanted to share with you a combination of work that'll hopefully give you a bit more insight on how to reduce embodied carbon in your work. So the question of the day, how do we reduce embodied carbon? The way we've been looking at this issue at Architecture 2030 is pretty similar to how we look at meeting operational code requirements. So within a building code, you have a prescriptive path and a performance path. The prescriptive path is essentially meeting checkbox requirements, so like window to wall ratio, R value, etc. And those requirements have really set the foundation for energy modeling programs that we use and we love today, and we use to demonstrate that our designs meet these requirements without necessarily going through the checkbox. We're allowed a bit of more flexibility in that regard. However, with embodied carbon, we've historically taken the opposite approach, and by historically, I guess I mean just in the last 15 years or so. But much of the work today has been focused on this performance path approach, which, as Anthony set the stage for, it really relies on EPDs and whole building LCAs. However, the data from the EPDs in this approach has been able to show us certain attributes of a material that result in lower embodied carbon, creating a prescriptive path, which a lot of what Anthony outlined in those material slides was this prescriptive path approach. So in this way, having these two approaches, we can really reframe how we look at materials in a way that is impactful, scalable, and actionable globally. So just as we have prescriptive and performance paths for operations, it's also crucial that we have both for embodied carbon as well. So today I'm going to dive into both approaches, starting with this performance path. I want to share a project I completed a few years ago while working with Allison Kwok at the University of Oregon. And then I want to talk about one of Architecture 2030's initiatives that utilizes this prescriptive path approach. So the research project I want to share with you, like I said, is one I did with Allison about 3 years ago at this point, in which we modeled and compared the embodied carbon impacts of several Pacific Northwest passive house projects. The reason we focused on passive house is that both Allison and I are certified passive house consultants. I began a CPHC about 5 years ago at this point, but also because passive house sets a very high standard threshold for operational energy performance. And we wanted to see what was the embodied carbon impact of that, and were there opportunities for reducing embodied carbon while still meeting stringent operational performance requirements. So how do we go about doing this? Right around the start of this research, Allison and colleagues published this Passive House Details book, which is an incredible resource, but it includes wall assembly details for many passive house projects in the Northwest and actually across North America as a whole. So I took six actually of these details and ran it through, or modeled them in Revit and then ran it through Tally, which if you're not familiar, Tally is an embodied carbon plugin for Revit developed by the design firm Karen Timberlake. And within Tally, you can control inputs like the type of material, transportation distance, etc. And it uses a database of EPDs and then multiplies the embodied carbon impact by the material quantity in your design. So I should note that typically you would want to do a whole building LCA, but for the point of this comparison, we simply just modeled a 5 by 5 foot area of wall assembly. So not the roof or the floor area, or floor assembly, which often have a much higher embodied carbon impact due to structural requirements, foundations, and as well as a much higher amount of insulation. And I also want to note that we used Tally 2017. Which does not have the same features that are available in the latest version of Tally. That would likely change the results slightly if we were to run it again today. So the first case study we looked at was the Stellar Apartments. This was the first affordable multifamily passive house in the US. It's located in Eugene, Oregon, and was completed around 2014. So from inside to out, and this detail would be from right to left, this wall assembly was JIP, a 2x6 stud with blown-in cellulose, OSB with the seams taped as the air barrier, and then outboard the stud was 4 inches of polyiso and fiber cement siding. The second case study we looked at was a single-family residential project in Portland. This was CH2. For this wall assembly, so inside to out is left to right here, we had gypsum board, let's see, 2x4 with blown-in fiberglass, plywood with the seams taped as the air barrier, and then a 9.5-inch TJI with blown-in cellulose, 1.5 inch of fiberboard, furring, and then fiber cement siding. The third case study we looked at was a very large multifamily project. This was Orchards at Arinco Phase 1, also located in Portland, Oregon. This from in to out was JIP, a 2x10 with blown-in fiberglass, plywood as the air barrier, 1.5 inches of mineral wool, and then it was finished with fiber cement siding and brick. For the purpose of this comparison, we chose a segment of the wall that used brick, since most of the projects actually used fiber cement siding. So we wanted a bit of a comparison there. And then we also looked at Orchards at Arinco Phase 2, which was the exact same wall assembly, also located in Portland, except they were able to reduce the thermal components of this envelope while still meeting FIA certification. So the 2x10 with blown-in fiberglass became a 2x6, and the 1.5 inches of mineral wool was reduced to 1 inch. And again, we looked at a portion of the wall assembly with brick. So the fifth case study we looked at was San Juan, another single-family residential located in the San Juan Islands in Washington. This one was completed in around 2013. So from inside to out, this wall assembly had JIP, a 2x6 with dense packed fiberglass, OSB with the seams taped as an air barrier, another 2x6 with dense packed fiberglass, so a double stud wall approach here, and then 1/2 inch of fiberboard, steel furring, and fiber cement siding. And then the last case study we analyzed was Skidmore, another single family residential. This is located in Portland, was completed in 2013. And from in to out, this one had a JIP, again, as always, a 2x8 with blown-in fiberglass, plywood as the air barrier, 3 inches of polyiso, wood furring, and then vertical wood siding. So how do they compare? This is normally where I would ask you what you think, which wall assemblies have the highest or lowest embodied carbon, or if you think they are all roughly the same. So I want you to think about that mentally, and then I'll share the results with you. So drumroll please. From lowest to highest, we have Orchards at Arinco Phase 1, Orchards at Arinco Phase 2. So you can see that the reduction in the thermal envelope did in fact reduce the embodied carbon of that wall assembly, not surprising. Then we have CH2 and San Juan. And from there we have Skidmore and Stellar. So you'll see some common groupings here. These first two were a wall assembly that had a stud and then exterior mineral wool. The second two here took a double stud wall approach. And then the last two here were a single stud with insulation and exterior rigid insulation. So they both used polyiso. All right, so this is great, but you're probably curious what materials contributed the most to each wall assembly's embodied carbon impact. So to dive into that a little bit, for Orchards 1, brick actually made a significant impact. Had we looked at fiber cement siding, this would probably be lower. But the brick alone was about 1/3 of that wall assembly's embodied carbon impact. Plywood, the 2x10 with fiberglass. Mineral, also a pretty significant chunk. And then JIP. For Orchards Phase 2, same amount of brick, so same amount of embodied carbon, same with the plywood. You'll see here the 2x8 with fiberglass, a slight reduction in embodied carbon from the 2x10. And then the 1 inch of mineral wool, a more significant reduction from the 1.5 inch. And then JUAN. For CH2, medium density fiberboard, this is surprising for quite a few people, but it actually has a really significant embodied carbon impact. And again, this was only 1/2 inch of material. Plywood. The wood furring. This is the 2x4 with fiberglass and the 9.5 inch TJI with cellulose. One note here, so CH2 uses a TJI, but that wasn't a material available within the TALI database. So for this study, we assumed a 2x10 stud. So even though TJIs have less material overall, they do require more manufacturing, more adhesives, and would likely result in a higher embodied carbon impact. Though I would be curious to see how much of a difference that would make. The fiber cement siding, so here you can see the difference between the fiber cement and the brick. Had we looked at a portion of the wall in orchards that used fiber cement siding, you could see it'd be a reduction there as well. And then JIP. For San Juan, so the steel furring, medium density fiberboard, again, a pretty high impact. OSB, you'll see OSB is higher than plywood for the same function within the wall. This is the double studs, the 2x6 wall assemblies with fiberglass, the fiber cement siding, and the JIP. All right, for Skidmore plywood, the wood siding, the 2x8 with fiberglass, 3 inches of polyiso. You can see it's almost half of this wall assembly's embodied carbon impact. And then JIP. And then finally with Stellar, we had OSB. Here they used a slightly different thickness, so you can see it's a higher embodied carbon impact than other wall assemblies. The 2x6 with cellulose, fiber cement siding, 4 inches of polyiso. Again, now almost 2/3 of the embodied carbon impact of this wall assembly, and JIP. So a few notes here. The variances you see in similar categories account for different assumptions. So for example, different densities of fiberglass affected the embodied carbon impact. Different thicknesses of OSB, for example, also had similar effects. So that to say, if you're using TALI and these tools as a performance path approach, the assumptions you make a huge impact on the results you get. So they say the tools are only as good as the user, but it is a good opportunity to get a better understanding of embodied carbon. I also want to note that the newer version of TALI offers the opportunity to include biogenic carbon, which this version did not. So including biogenic carbon for timber products and also for cellulose, for example, results in a lower and often negative embodied carbon value because it's giving a credit for the carbon sequestered by the tree during its time growing. There's a great tutorial on this topic that was done by TALI. I'd be happy to provide the link to that. I should have included it on the slide, but the newer version of TALI does include that opportunity, and it does make a pretty significant impact. All right, to conclude this portion, as you can see, blown-in cellulose and fiberglass had a lower embodied carbon impact than rigid insulation. And I should clarify here in case it's needed, blown-in is very different than a blowing agent. And so there's a very significant difference there. Other conclusions, so polyiso and MDF, the medium density fiberboard, were major contributors. Mineral wool also had a high embodied carbon impact. However, you could see in those first 2 orchards at Orinco wall assemblies, it was lower overall than the other wall assemblies. So if you have to use a rigid insulation for climatic conditions or whatever, it's probably best to choose mineral wool over polyiso, EPS, and especially over XPS. And then again, a reminder that this study only addressed wall assemblies, so it's equally important to do a whole building LCA, look at the roof and floor enclosures as well. And a quick thank you there to Alison from the University of Oregon, TALI for the educational at the time license, and then the firms for sharing their construction drawings. All right, so really quickly, I do want to talk about the other pathway for embodied carbon reduction, which is the prescriptive path approach. So a bit of backstory, 2 years ago, we were talking about this issue within our org, Architecture 2030. And at the time, there was a really limited amount of EPD data. And what was available was really only within North America and Europe. So the tools that were available, and at the time, the tools that were available were not necessarily free. There are a few free tools, but for example, TALI, you have to pay for it. To use it within Revit, you have to pay for Revit, that kind of thing. So we kind of saw a huge barrier to entry for most designers and really for designers globally, especially knowing that the bulk of new construction between now and 2050 will take place in the global south. So Asia Pacific, India, Africa, Latin America, South America, that kind of thing. However, we were thankful for EPDs and the data that was available, as it helped us understand the materials that were used, and that understanding helped us develop this carbon smart materials palette. This is a free, high impact, globally applicable, and immediately actionable pathway for embodied carbon reduction. So the carbon smart materials palette identifies the attributes of a material that contribute to its embodied carbon impact, and it provides strategies for reducing that through design and specification. The palette is categorized into high impact building materials, which are the predominant building materials being used today that have a high potential for embodied carbon reduction. And we recently added carpet and gyp. I should add, we added them back in March. It includes carbon smart materials, which are naturally low carbon or carbon sequestering materials. You'll see one note, wood falls into both categories for a variety of reasons. But also the three materials here, hemp, creep, sheep, spool, straw bale, those are all opportunities for insulative materials. So keep that in mind. And then the last category here is a whole building approach to emissions reduction. By taking this course and focusing on existing buildings, you're already making great strides in embodied carbon reduction. That's the very first thing that we note in that swatch. And I think, as Carla Elefante says, the greenest building is the one that's already built. So each material we call a swatch of the palette. Each material swatch contains an introduction with information on the carbon impact of that material or material category. It also talks about carbon smart attributes. So what qualities of the material or manufacturing process can be used to reduce embodied carbon. And then the second set is design guidance. So how do you design with that material to reduce embodied carbon? And then several of the swatches also include this acknowledged challenges, questions, and unknown section. I should note that the palette is a living document, so it's intended to be updated over time as more information becomes available, as technology advances, that kind of thing. For example, we recently updated the concrete swatch, and we're working on updates to the wood swatch currently. But for insulation in particular, an example is that an acknowledged challenge would be the balancing operational performance with embodied carbon impacts, as well as the fact that insulation decisions are highly climate dependent and situational dependent within the project. So just to dive a bit into each material, and thank you, Anthony, for for focusing on aluminum and glass, so I can cover the rest of it. But so for concrete, for example, the most impactful thing you need to know is that less cement means less carbon. You can often use cement as a proxy for global warming potential. So if you reduce the amount of cement within a mix, you're going to be reducing the embodied carbon impact. So for this one, we recognize that it's typical practice to specify like a minimum amount in cement and or a maximal allowable amount of SCMs. Instead, we're saying flip that around, specify a maximum cement content or specify the required compressive strength at a specific age. Those are opportunities for reducing the embodied carbon of concrete through specification. For steel, specify steel with a high recycled content. There's two different manufacturing processes for making steel. One creates what we call, I guess, virgin steel. So it's using the raw materials to create a new steel product. And the other manufacturing process, which is an electric arc furnace, similar to aluminum, like Anthony was saying, it recycles existing steel into new steel products. And the electric arc furnace is about 5 times less embodied carbon impact than the basic oxygen furnace, which creates virgin steel. And so if you're specifying steel with a high recycled content, you know it's going to come from an electric arc furnace. And because it's an electric arc furnace, it's powered by electricity. So similar to the grid mix information Anthony shared, where you're getting that steel from does have an impact. And there are opportunities for getting steel manufactured using completely carbon-free renewable energy. There's actually a handful of steel mills within North America that do just that. For insulation, use natural materials. There are so many materials that naturally sequester carbon that can be used as insulation. So look into them, start incorporating them into your designs. And also using blown-in applications. And again, this is different than installations with a blowing agent. So blown-in fiberglass and cellulose, the reason we recommend this is because if you're using batt insulation, it can often slump, which means it's kind of settling over time. And that can lead to thermal bridging, which can lead to moisture condensation, which can lead to assembly degradation, which increases the embodied carbon impact because you have to replace that material. So what we found is if you're using blown-in insulation, it actually kind of reduces that potential. And the last example I'll give is for wood products. There's a lot of things I could talk about here with wood, but especially for people on this call, I think my biggest recommendation would be specify locally harvested and manufactured wood products. If you're in North America, you're going to be getting wood products from sustainably managed forests. Of course, some forest practices are better than others. We could spend a whole webinar talking about that, but I think the highest impact thing you can do is procure local products, and that's because transportation emissions is one of the highest impacts of embodied carbon emissions for wood products, and also because if you're getting local products, you have more insight into the forest practices that are being used, and again, you have more insight into the grid mix as well. And I point out grid mix because about 16% of energy consumption in a mill is electricity based. So if you're in BC, you have a cleaner grid, it's going to have a much lower embodied carbon impact than if you're getting a wood product from, say, Calgary, which is mostly a coal and fossil fuel based grid. So. All of this and more is freely available at materialspalette.org, or you can just Google Carbon Smart Materials and you'll find it there. And the last thing I want to do is give a really quick plug for an upcoming event. If you're interested in embodied carbon, Architecture 2030 is putting on a global teach-in. So it's a free one-day event in September that'll focus on reducing the carbon impact of the built environment. And there's a whole track dedicated to just embodied carbon. So you can learn more about that at carbonpositive.org. With that, thank you for your time, and I really look forward to any questions you may have.
Great, thank you so much, Lindsay. A lot of great insights there. Very helpful to especially hear the importance of having both approaches, prescriptive path and also performance-based path for considering embodied carbon, and also very useful to see that comparison between different wall assemblies. I was wondering if that report is available to share with our attendees. Is it publicly available, that study?
You know, it hasn't been published or anything, but I'd be more than happy to email it to anybody that's interested and share these slides as well. So
yeah, that would be helpful. I'm personally interested, and I can see that several people are asking for that in the GoToPanel question section. Great. So with that, I am going to invite our next speaker, Graham, over to you.
Well, hello everyone, and thanks for the last two presentations. They're absolutely fantastic. And what I'm looking at here is a case study of a project that's under construction. It's the interfit of an 18-story building, and looking at an overview of what's been achieved, but then also some decision points where how can you, in the thick of it with your contractor and during value engineering and with the owner, be able to land on some of the decisions of the great data that we've seen today. So the context for this is a broader tower renewal project that we've been working on with a series of partners across the country, and it's looking at this era of high-rise buildings. So the bulk of high-rise buildings in Canada were actually built in the 1950s, 60s, and 70s. So the massive condo booms that have happened in Vancouver and Toronto and elsewhere haven't yet caught up to the first round of high-rise construction. And these buildings are generally affordable, generally the bulk of the purpose-built rental stock, and they're all aging at the same time. So a lot of the focus is how do we make sure that we don't lose this stock, it remains affordable, but crucially, it becomes climate resilient. So this is some of the data looking at all high-rise housing across the country, and the navy blue is the one that we're focusing on. So if you look at Vancouver, it's almost a third of the different eras of high-rise housing, including the older 60s stock. But if you look at the Toronto stock or Ottawa or elsewhere, the majority of high-rise housing is that first generation. So that's the focus of this. It's about 700,000 units across the country. And some of the aging is becoming critical. So we're finding some buildings that are simply having to go offline because of failed systems, failed electrical systems. The elevators are routinely failing, and how, especially in COVID, with people sheltering in place, it's become quite an acute issue of there's an imperative to keep these buildings going in a way that's healthy, appropriate. And now looking at through the lens of embodied carbon, how do we do it in the best way possible? So a lot of our focus is how do we make this work? Doing retrofits like this is highly capital intensive. So you need the finance structure in place. You need the standards. And this conversation today is really what are some of the metrics of standards by which owners, decision makers, and designers engage in setting the specifications for these projects. And you need a retrofit industry that's ready, especially a retrofit industry that can tackle buildings with residents in place. So a lot of this has been a lot of policy pushing and activism and making voices heard about that this is an imperative and how do we push, push the players and the stakeholders to be able to bring investment to these buildings. And a major victory has really been with the National Housing Strategy, which launched a repair and renewal program of several $1 billion to be able to kickstart the first generation of deep retrofit across the country. And we have a fantastic leadership in Hamilton Housing, just outside of Toronto, who have a passive house and low energy mandate for their entire stock. They have a new building program going for new buildings, and they also, looking at their existing stock, wanted to engage in interfit. So we've worked with them since 2017 to engage in feasibilities and to work with them to put the applications together for grant funding and everything else to be able to reach this goal. And it's really through the leadership of that organization. And Hamilton is a really interesting city in that in Eastern Canada, it has the highest number of passive house buildings happening. So on the other side of the mountains, Hamilton seems to be the epicenter of passive house activity. So it's a 1967 building, 18 stories high. This is it the year it opened, and this is it just a few weeks ago under construction. And you can see there the air barrier up and the windows going in. And so what I'm going to do now is provide an overview of our objectives and as designers what we needed to do to meet budget and to meet client needs. As anyone who's done a deep retrofit knows, it's sort of like going into a cruise ship. You're dealing with layers and layers of equipment, and you're figuring out what can we keep, what needs to be replaced, and how do we do this in a way that's not terribly invasive and meets timelines and project requirements. And so because of the funding and because of the ambitions of the owner, massive greenhouse gas reductions, through Interfit, 20% of units are going to be retrofitted to be fully accessible, and of course affordability. And we did that through systems, envelope, and general modernization, but not just getting to low energy. And so what was great about the Interfit standard, and because it's embedded mainly in sort of German and Middle European building codes, there's a huge emphasis on comfort. And really, when we're looking at buildings like this, how do we engage in retrofits that lead to tenant comfort? We all know you can make a low energy building that's terrible to live in. So that was, and life safety and community connectiveness and all of these other pieces. So this was sort of our brief in looking at this building. And so this is a typical unit. This is a long list of all the things that were deteriorated, including huge amounts of asbestos, mold embedded in walls, completely deteriorated soil stacks. So there was a massive state of repair piece, but then also the layers of achieving Interfit. So, a big winter coat on the outside of the building, triple glazed windows, and a strategy of active and passive ventilation to be able to provide both heating and cooling to the building. And it's a seniors building, importantly, and it was very critical that we maintained comfort. So cooling and a light active cooling strategy was required. And the difference between this image and this image is the major works required to provide a barrier-free unit, which is quite a bit of work in there that was a mandate to the project, but quite a big part of it. So looking at the envelope. So when we first started this project, this is what it looks like. It's sort of block wall with masonry veneer, very robust. We imagined we do this from the exterior. So achieve our R38 effective wall. It was a layer of mineral wool and then a layer of mineral wool ephes on the outside of a sheathing layer. So a sort of a double ply wall. And to make that work, we had to have fiberglass clips and a large thermally broken structure to do this. So that was the first strategy. When we got into investigations, we realized there was pervasive mold throughout the interior walls. So for better or worse, we had to gut the inside of the building to remove all of that wall, which provided a much more simple wall assembly, one you couldn't do with residents in place, but one that made sense in this particular project, which is, and importantly, is empty. The building was actually decanted of residents because of the poor state of building quality before construction. So it makes this project a bit of a prototype to say, how would we then do this in a building that's occupied? And then, of course, as all passive house designers know, there's the exhaustive process of meeting your target and getting your PHPP and getting your pre-certification. And so we looked at a whole series of things, from metal clips to fiberglass clips to where the plane of the window was, and landed on our pre-certified design. And another one piece where we certainly are contributing to embedded carbon is we made the decision to remove the balconies. And the reason for that, through a whole series of studies, is that the kit just isn't available in North America as it would be in Germany or Sweden or other jurisdictions for ready-made balcony enclosures that would have the thermal performance for interfit. So after long discussions, and a main one being there was about a foot drop to make sure that they're actually accessible and barrier-free for a seniors population, the owner decided, let's remove them and make sure we have a thermally tight envelope. But that certainly won't be the strategy for each of these buildings. So it's innovation required here. And this is a look at some of the windows going on. This is the air barrier, which is fluid applied. And then the mineral wool EFIS will go on top of that. It's a 6-inch buildup. Then into the ventilation strategy. So we piggybacked off the existing system using the existing cavities throughout the building, putting in new distribution and bringing in direct ducting into each unit, as well as sprinklers into each unit as well. The building hadn't been sprinklered. And so this was interesting. So we really debated unitized versus centralized, and we ended up going centralized in this case because of the point tower configuration made it work, but also the owner, as it's a rental building, didn't want to have to change 147 filters, so really encouraged us to go, and they were about cost neutral. So in this case, it was a centralized system. This is some of the heating and comfort studies we did with our the major consultants on this project. One is JMV Consulting, which is a Vancouver Island base, really fantastic Canadian consultants who recommend everyone work with, and as well as TransSolar out of Germany, who've done quite a bit of these high-rise interfit projects. And it was really looking at not just meeting the interfit standard, but looking at what from each exposure is the effective comfort that we'd be achieving. So this was a driver. And then this is looking at our graduated cooling strategy. So ceiling fans through ventilation, but also a centralized dehumidification and light cooling, and then a cooling boost within each unit, as well as a heating boost within each unit that's directly resident controlled. One of the issues, we wanted to do exterior shading. It was too expensive to bring over sort of European style exterior shading, so we've gone with interior blackout blinds, but with an 18% window wall ratio, it passed all the interfit requirements, thankfully. And we also modeled performance on 2020 projected data. So we weren't looking at the present, we were looking at the future and ensuring comfort. And this slide I think is quite interesting. This is one of the resilience checks that we did. This is looking at some cold temperature. So the way to read this slide is that the bottom is the in Celsius, the outdoor temperature. So imagine it's a cold day in February. The blue would be a building code, or Ontario building code, in this case, compliant building, and the yellow is our building. So the idea is that if power goes out, according to public health, if the building goes below 10 degrees Celsius, you have to evacuate. So that means this building, if the power went out, would have to be evacuated within 1 day. Our building, with the interfit, would last 5 or 6 days. So that's one of the considerations beyond energy performance that goes into, for the owner, was very important. So decision points for embodied carbon. There were a few of them. So one was fuel switching. So this was discussed, and this is a lovely slide I pulled from the Ontario Power Authority and about the coal phase out. So Ontario's grid is a mix mostly of nuclear, but since the coal phase out, it's become competitive with other Canadian, mostly hydro grids, and extremely competitive compared to what you're seeing south of the border, where it's mostly coal. And so we were able to look at some of the metrics that were discussed earlier here, and to say, even though we're meeting Passive House in terms of energy per square meter, let's fuel switch for heating and go to heat pumps in order to go to electricity. We wanted to pull the gas line completely on the building, but we are prevented to for domestic hot water. And it was to heat domestic hot water electrically, unfortunately, would require a larger transformer than was available within the city district. So it was a logistical issue outside of our control. So the only gas in the building was domestic hot water. The next one is envelope. So envelope was quite a discussion, and the issue, a big one, was safety. So after Grenfell, and myself and my team was actually in London when Grenfell happened, and we were meeting with building officials and touring sites for other reasons, and then became kind of embroiled in it. And it was quite a intense experience. And we're actually able to meet with the fire marshal and others when this was all happening. And while each systems are permitted in our building code, we felt, and the owner felt strongly, that they wanted no combustibility whatsoever on the exterior of the building. So for that reason, we designed this as mineral wool. And then the added value was, when we did similar analysis to what was discussed earlier, there's such a compelling embodied carbon argument, which really, you could make the argument that if we had gone with EPS or another system, what's the point of even going interfit? So I think that the data and the standards, and to build into the standards an embodied carbon argument or metric is absolutely fantastic. And the other one, of course, is demolition versus renewal. So every time we do a retrofit project, there's always the voice in the room that says, why don't we tear it down and rebuild it? It would be faster and cheaper. What we found in our set of projects is that it's neither. In terms of cost, even with doing this interfit project, which is highly ambitious, and it's nearly an entirely new fit out in the interior, it's still substantially cheaper than if we had torn down and built a new comparable building. And then, of course, the social costs if these buildings are occupied. And then there's the embedded carbon discussion. So this is a very hot off the press, relatively crude, but I'd love to work with the group on this panel to flesh this out. So JMV, our Passive House consultant, did this for us. And what we're looking at here is actually saying the blue line is that what if you demolished our building and replaced it with a Passive House certified building, so a very high performance building. The orange line is the projections of our interfit building. And so what it's suggesting is it would take 180 years until the tearing down and rebuilding to Passive House standard was competitive in terms of embodied carbon to what we're doing here with interfit. The monkey in the wrench with this is the gray line is actually the building if it just kept on operating. One thing that's important to note is that these buildings are enormously energy intensive. So the buildings that we look at have an average energy intensity of around 350 kilowatt hours per square meter. It's just, single glazed windows, all natural gas heating. So it would only take 18 years until tearing it down and building as a Passive House would be carbon competitive. There's, of course, cost and social other reasons, but we'd like to plot the one, if you just did a code compliant building rather than a interfit, what that date would look like. So this is the building. It sort of makes a compelling argument that this is the way that we should go with retrofits rather than tear down and build new. And if we looked at the stock countrywide, I'd love to do this for embedded embodied carbon, but just for operational carbon, you could cut up to 3 megatons annually just from the gas loads. And we're working with CMHC on this on a longitudinal study following, looking at some energy and non-energy benefits. So I'd love to share that once that's released post construction. And also we're engaged in some studies really looking at when you do a project like this with retrofit, you realize that there's a lot of products and materials that simply aren't available yet in our marketplace that we know are available in Europe and elsewhere. But because of the advancements of the STEP code and the great work happening in BC, we were able to spec all North American and largely Canadian products for this interfit, such as Cascadia windows and some other HRVs and some others that weren't available even a few years ago. So our industry is advancing rapidly. There's still strides to go. And another piece is looking really carefully at means and methods about engaging in a project like this with residents in place, which is an entirely different, a different set of solutions. So thank you very much. That's my presentation.
Awesome. Thank you so much, Graham. It is always wonderful to learn more about Ken Sobel and really seeing how strong leadership, in this case at Hamilton Housing, can make it possible to design to such great performance levels in retrofit projects. Thank you for sharing that project with us. Now I am going to start the Q&A, but before that, I see very interesting questions coming up in the Q&A. Just before we get to that one, there is this poll that we have for the audience. We want to know, what do you think about the key barriers to advancing the case for embodied carbon reduction in building retrofits? If you can take a couple of seconds to think about it, and then we share the results with everyone. Awesome. Here are the results. The majority voted for lack of embodied carbon policies specific to retrofits as key barriers. And then after that, on familiarity with carbon impacts of building materials and lack of a guide to reduce embodied carbon in retrofits have been identified as key barriers by the audience. Thank you so much for taking the time to answer here. Now I'm going to invite all of our speakers to the panel for Q&A. Great. Okay, there are lots of questions that the attendees submitted, which is great. I'm gonna see how many of them we can cover in the time we have left. The first question I wanted to ask you all is, what do you think are the barriers to designing with low embodied carbon materials and system components? And secondly, what market or policy drivers do you think can move clients and design teams to include minimizing embodied carbon as a key project objective in our retrofit projects?
I'm happy to jump off if that's okay.
Please, go ahead.
Well, I thought your poll was excellent. So all of those are ones that I would agree with and probably ranked similarly to the audience. I would say that policy is key. When it comes down to tough decision making and the tough value engineering discussions that always happen after you get your final costing, and the client realizes that they're short. We've been involved in several projects where suddenly the initial ambitions of the project slowly get eroded away, and the only thing that prevents it is key policy. So in terms of base code or whatever it is, whatever the bottom threshold is for that particular client, we're really projects that are passive house or where certification is required is fantastic, because that becomes a driving force. It becomes something that you can actually point to the contractor and to the owner and to other decision makers and say, if we do X, we won't get certified, so therefore we have to do Y. I think a similar framework that related to embodied carbon would be perfect, and it's really heartening to hear that the step code and other things are going that way. I think that there's been some work that we've been involved in to some extent about the model national building code for existing buildings. And there's a lot of work to do around any guidance around retrofits in terms of energy performance, and especially embodied carbon. So I think it's really there. How is there a model code that then goes into provincial or city-based codes that sort of toe the line and create that, that expectation? And then that gives designers an ability where I can, call Lindsay or call Anthony and say, hey, we need help. We need to push this because it's a project objective, and really changing it from a nice to have to a must have. And then following that, then it gets to the other things on the poll, which are awesome. Now that I have that objective, where's the data? Where's the supply chain?
Thanks, Graham. Anthony, Lindsay, you wanna?
Yeah, I'll just a quick point of follow. I totally agree. Like the policy definitely is a big driver, and one way to ease into it, I think, like what Vancouver did is actually a really great approach in that they looked with the rezoning requirement. I think it was 2017. They required disclosure of LCA results and also doing it early in design too. So not just like something that you do at the very end. And I think that builds up a lot of like industry competence locally, but also like it just kind of puts everyone in the same field. Like how to say it, all the design team members, they start looking at these results. I think that's a great first step. And so if you're in a city that obviously if you're working with a municipal policy, that would be a great step. But even if you don't have that, like working with your clients, if you have a progressive client or it's an institutional client, I think they can also follow similar approaches. So obviously you can go with one of the green building standards, you can go, zero carbon building standard or ILFIs or LEED. And even if you don't have those standards for yourself, you could, from a client perspective, they can also mandate and say that like, we want to push for, at least a certain percentage reduction in embodied carbon. I think that, especially when we get to the point where we're talking about percentages reduction in embodied carbon or some sort of reduction criteria, that's when the thing really shifts. Because right now, even when you're in disclosure, like oftentimes people don't look at the results. It's like, okay, we're just checking off a box type of thing, right? But as soon as you tell them you need to hit some sort of reduction threshold, that's when people start paying attention and it actually makes its way to the design conversation.
Very true.
Absolutely, I would agree with all of that. And I think the code itself is more of like a stick to push you along. There's a lot of things you can do as a designer, as a contractor, to take the initiative upon yourself. Like make the commitment within your firm. For example, the 2030 commitment is now incorporating embodied carbon. If you're an engineering firm, the SC 2050 commitment is phase out of embodied carbon by 2050. Sign on to these commitments, make it a firm commitment, and really push it, I say, within your own org.
Yeah, they're very great insights. As you all mentioned, and also the audience referred to, there are some barriers to really consider embodied carbon in our building projects, but there are some solutions as we discussed today, and hoping that we can push for them. The next question I have, somehow as a follow-up, I wanted to know what rationale should be used to set embodied carbon targets for building retrofit projects. Imagine that there's a client that wants to really care about embodied carbon and want to know what sort of performance target would make sense. Do you have any suggestions or recommendations what that could look like, or what process should be followed to set a target?
Sure, I can speak to that. I mean, this is just off the top of my head. Obviously, when you're talking about retrofits, you're not demolishing the initial structure, so there's obviously a benefit to that. And I guess the challenge is sometimes then like estimate, like, are you going to do an LCA to figure out what the impact of the original building is or what a new building would be? So that like there's a certain thing that you can frame the argument around that way. But if you're also looking at just purely on the retrofit side of things, you could also kind of follow a similar approach to whole building LCAs. Like if you're designing for new construction, where you're saying we're just targeting a certain percentage reduction in embodied carbon, and just for the retrofit, so just for the new additions to that section, let's just look at that carbon and then set some sort of percentage reduction that makes sense. You could follow what LEED's doing or ZCB or any of the other standards, like 10-20% or something like that, and that would be a great way of kind of framing the conversation, knowing that obviously there's additional benefits from just compared to building new.
Yeah, I think those are really good points. And I think it comes down to what are the objectives of the project? And obviously when you're dealing with housing retrofit, for instance, there's multiple objectives, and it's really, tenant health and comfort and longevity of the housing thing is first. And then as an equal co-benefit is climate resilience and everything else. And it's, it's that client-driven Venn diagram that we all as designers, push and provide data for. And so what I think would be really captivating is just the key decision points around providing the literacy and the data that I think a lot of people would find surprising. Like I think a lot of people would find the slides that you guys shared to be very surprising, right? And to make that just part of the dialogue, to sort of have that carbon budget and to say, great, we've kept the building, so we've saved this much. However, if you go with polystyrene, exterior, you might as well not do the retrofit project for an energy perspective, right? So I think it's almost setting what is that budget, and then how is there a heads-up display about embodied carbon as that? Because I think what's so captivating about this discussion is that if you exclude embodied carbon, it's only partial data. So you're living in a bit of a fantasy to say, well, we saved this much on natural gas, it's a great project, but we smeared the building in a petroleum product,
Mm-hmm.
Yeah, absolutely. I would second all of that. I think you don't necessarily need a target. I mean, if you have the intention to just reduce embodied carbon, there's a lot of tools out there that show you how to do that. If you want to show and demonstrate you're meeting that reduction, there's a ton of, you could use Tally, OneClick. EC3 is a great free tool now too that includes various benchmarks. So the CLF study that Anthony shared is incorporated in there. And then the 2030 challenge targets for embodied carbon are now incorporated in the next version. So there's a lot of tools out there if you want that.
Mm-hmm.
Just to follow up, I think what always becomes the challenge is cost versus performance. And I think the most important thing is really just to make embodied carbon and clear data to be as easy as, usually there's cost and then energy performance, but if there's also embedded carbon and you're looking at it to say, this may be X more expensive, however. And I thought that in both of your presentations, just the clarity of data was excellent. And I think that's one of the huge things is how is that just pervasive? How do we mandate it that when you buy a product, it has its embodied energy or embodied carbon right on the package?
Mm-hmm. Yeah, and then there is a question submitted by one of the attendees, which is relevant to this point. Is I'm going to read it here. Do we have comparison between the efficiency of the insulation versus the embodied carbon of their production? Where is the sweet spot?
Yeah,
I think that was originally, yeah, go ahead, Lindsay.
I was going to say, and Anthony and Graham jump in, but you can kind of do that if you're using a combination of tools, like say I'm using Sapphira for energy consumption plus Tally for embodied carbon. You can kind of make adjustments and see what changes. There's a whole host of people as resources that I know of for that, but I don't know if one comprehensive giveaway on that, but I don't know, Graham and Anthony.
Yeah, no, I agree. So part of the challenge is that you have energy modelers that kind of do their own separate analysis, and then you have people doing the LCA, and then sometimes it's the architect, the structural, or it could be the envelope consultant, or it's like an LCA just a specialist or whatever. And so we definitely do need to marry those two analysis and look at similar options and whatnot. And I think right now that's definitely the next step to take. I think right now we're trying to get people to just take even the first step of looking at embodied carbon, but then for sure, once you're actually looking at it, the obvious question is, how does it compare between those two options? So, when I had that one chart in my presentation looking at the R values, insulation broken down for different types of insulation. I hadn't seen that chart before. So it actually took me a lot of manual digging of data to just kind of frame it in that way, right? And I think just having that data, bringing that into the conversation, and then also getting kind of the energy modelers' feedback on that. It's more of you got to bring the different stakeholders together to kind of have the conversation around that to figure out what makes sense for different projects. But I think it requires some modeling to actually figure out the answers for those.
Mm-hmm. And a lot of that, I was just going to quickly say that Lindsay's reports that we will be sharing hopefully with everybody is a good example of saying how different choices of, let's say, insulation or different components of wall assembly would impact operation, and what does that mean from embodied carbon perspective. Go ahead, Graham.
No, I was going to say, and I think there's nuance, and there's definitely that sort of sweet spot where you have to, you know, have the Venn diagram of modeling. But also, I think some of it's pretty black and white. You know, like some of it is pretty clear as to the top of the graph versus the bottom of the graph. So I think even in terms of what not to start with, and then you get into some of the more comprehensive assembly models that Lindsay put together. But unfortunately, it tends to be that the ones with the highest embodied carbon are the cheapest. You know, so there's also kind of a market transformation piece around how do we make those unattractive in terms of they don't meet certain metrics, so therefore owners decide not to use them.
Mm-hmm.
I'd say like
Thanks
that's
for
a common assumption on the cost vector, but I think that's not necessarily always the case. And I think that's just like, I feel like people jump to that conclusion, but we actually need better studies on that, I would say, to figure out. First off, most people don't know what the low embodied carbon options are. Like for instance, for insulation, that like many people don't know how, like what the order of magnitude for different types of insulation are, right? And so like we need to marry that with the cost data, and the cost data is changing and whatnot as well. So it's, I think we just need to first kind of look at that information. I agree, like we definitely need to marry those two, but I just caution against having the assumption that they're higher costs.
Well, I think an example there for sort of industry advancement is that we specified rock wool EFIS, and so with Roxol, and rock wool EFIS exists, but it's used for a very specific purpose. It's when there's two windows face to face for a fire rating issue, but no one uses it for a whole building. They do in Europe, but not in North America. And so when we specified that, there was a total confusion from the trades. They're like, no, you don't mean that, you know, you mean this. And it's like, no, we actually want the whole thing. And rock wool, and even rock wool now is very excited because they say, okay, you could use this for the whole thing. This is actually a lower cost, high performance product. And it's almost like reframing it, like an existing product you can use in a new way. We're just, because no one was specifying it, everyone was scratching their heads. But there is a delta, you know, it is more expensive to do rock wool EFIS versus poly EFIS or XPS or whatever. It's not a huge cost, but it is a cost. And in a culture where cost is king, it's like that other variable that helps that decision. It's pretty compelling.
Yeah, thanks for all your insights here. There are way more questions to get to, but unfortunately, because of time, I am going to stop the Q&A at this point. And just going back to the original slides, there are a few highlights I want to bring up here for the audience to learn about some upcoming opportunities. Well, as I mentioned, we will be, well, this Reframed initiative that I introduced at the beginning is this larger project, and this webinar series is part of that initiative, which was formally launched a few weeks ago, and we are kicking off with an RFP expected to be released this summer. We will be looking throughout the RFP. We will be looking for multidisciplinary teams to develop design solutions for low-rise residential buildings retrofits in BC, Lower Mainland, or Victoria area. And as part of the project, the selected teams will participate in a 6-month exploration lab with supports from climate, energy, and health experts. If you intend to answer the RFP or want others to know how your company can contribute to a proposal, we invite you to log your information at reframedinitiative.org. We think this is a team effort that will draw experts from all groups, such as architects, engineers, contractors, LCA modelers, energy modelers, monitoring and equipment control specialists, etc. The information you log in into the website will be shared online to help industry discover the amazing innovations and ideas that are out there that could be embedded in developing deep retrofit solutions. You may have gathered already through today's discussion and the previous 4 webinars as part of the Reframed Tech Series that we are particularly interested in retrofit solutions that integrate technologies and solutions such as prefabricated exterior wall, high efficiency and low carbon materials, as well as high efficiency mechanical system, seismic upgrades, climate adaptation measures, system controls and performance monitoring. So these are the throughout our webinars in the Reframed Tech Series, you have heard particular technologies or solutions or performance areas that we are interested to explore during this upcoming demonstration project, which will be reflected also on the RFP. And with that, I want to thank you all for joining us today. And it was great to hear all the presentations and great insights shared by the speakers. And also, I want to thank our audience for this great set of questions and your answers to the poll. If you have any question, please write us at connect@reframedinitiative.org. And with that, I close this session today and hope you all have a great day. Thank you.
Thanks a lot. Bye.
Thank you.